I returned 2 sets of homeworks to you, and I hope that there aren't any questions in that, and I'm hoping that on what we had due today, that there were minimal problems. That was in scientific notation. Is there any discussion of any of the homework problems? A rare morning. Okay, with that, would you pass them over to the side and we'll have another go at it? Another set of problems to grade. And I'm going to ask you to recall prime factoring this morning. So we're just going to take a look at a number and remind you of the process that goes with it. We want to write a composite number as a product of primes. It's something I'm hoping that you're at least fairly comfortable in doing. And so maybe we could take something like 1,728 and write it as a product of primes. 1,728. And I'm just going to go through a little presentation here. It's very similar to what I do with the Math 10, where we list a number of the primes and go through an algorithm that's fairly commonplace in what we talk about as a product of primes. And we've looked at this, I think, a little bit earlier in the semester. We did that when we were reviewing fractions and what we did for finding common denominators using a product of primes. So let's take a look at a problem here where I'm going to take 1,728 and I'm going to write this now as a product of primes. So the first thing I do is list the primes that I would use in this process. And the primes, of course, a reminder, go forever. So this is just a partial list. And what I usually do is start somewhere down in here, low part of the page, and I want to divide by my smallest prime. And 2 being the smallest prime that will divide 1728. So I go ahead and do a short division here and get 864. So I'm arguing that you pretty much do the subtractions in your head. You could argue at this point that 8 times 2 is 16, leaves a remainder of 1. You put the 1 next to the 2 and go for that. But then we again are going to divide by 2. And we continue dividing by 2 until we can't divide any further. And so we get a 4, a 3, and a 2. Again, I divide by the 2. I get 2, 1, 6. Again, divide by a 2. And oftentimes, this is where an error creeps into this process, because we should get a 108, and sometimes we instead get 18, because we forget about needing the placeholder. And of course, if you get the 18 there instead of 108, you're immediately into an error. Well, we go with that again, and we get a 5, 4. We do that again. We get a 2, 7. And we note that 2 will not go into the 27 evenly, so we go a 3, we get a 9, we get a 3, I get another 3, and I end with a 1. Now that's just a fairly typical, rather tedious process, but we then argue that we can write 1728 as a product of the 2's and the 3's. And so up here I get a 2, and I ask how many 2's I have. So I have 1, 2, 3, 4, 5, 6. So I have 2 to the 6th, and then I have what? 3 to the 3rd. And so we argue that we have written 1728 as a product of primes using exponents as the process. Now in that same sense, we can call this factoring. So we are factoring 1728 into a product of primes. And if I were to, with some of the things we've done this last week, where we talked about trinomials, and in particular we talked about a trinomial perfect square. If I looked at something like x squared minus, and let's just take 6x plus 9, like 1728, I would like to write it as a product of what would be like primes, but we think of it as a product of linear factors. So what I'm getting at is you can look at this and say, well, that's x minus 3 times x minus 3. Now, that's recognizing that the first term here was a perfect square. recognizing the last term is a perfect square. And then the question, if we work backwards, if you were to take this product, you would get what? The inners and the outers, giving you negative 3x in each case, which would be your negative 6x. And so I have written this trinomial, which turns out to be a perfect square, as a product of these two binomial factors. They can't be broken down further. But just like up above, I wrote powers of the primes, I could think of writing a power of that binomial. So I'm hoping that you see those as somewhat similar. Now, if you didn't recognize that this was possible to write it as x minus 3 times x minus 3, you don't have the same luxury of saying, okay, I'm writing a list of prime numbers, and I can start dividing by the prime numbers. Obviously, if you did take x minus 3 and for some unknown reason thought it might be a factor and didn't recognize that this was a trinomial perfect square, you might be inclined to do a long division in the same way. And you might argue, well, how would you know that it was an x and a 3? Well, I had an x squared here, so I know it has to start with an x. And if I'm going to have a 9 out here, there are only a certain number of things I can try, an x minus 1, an x minus 9, an x minus 3. I look at the factors of 9. And of course, this does become, in the process, exactly what we wanted, another x minus 3. But just a comment here, as I looked at your papers, it appears many of you feel very confident of yourself without showing the change in signs. I didn't see this happening all that often. And that may indeed be enough for you to get by. But it's just a caution again. This sign change that goes on down here is one that's going to trap you oftentimes. So at any rate, x goes into minus 3x minus 3. And so this is what we were doing in the papers we just finished. And of course, we change these signs down here before we add and get a 0 at the end. So if you look at it as a similar process, I could use division to write a trinomial as a product of what we consider prime factors, in the sense that they cannot be broken up further. Well, that's the process called factoring. And most of the time, it depends on your insight to see a trinomial or some other expression as a product you recognize from the past. So what I'm getting at in this problem is this kind of thing we've talked about before. If you know 5 times 7 is 35, when you see 35, you know you have a set of factors. It's only when we get very difficult looking expressions like 1728 that you can't just automatically go to the prime product or the product of primes. Now, I'm going to make a comment here that is in the future, in the sense that it's not something I want to look at in any great depth. But I alluded to it when I said how you might know that x minus 3 is going to go out here. The x was no great problem because we know it's going to have to be x times x. It was the 9 that was not clear. So I could have tried the 3, a1, a9, and lucked into possibly the correct factor I needed. There are going to be problems in your future. I feel like we're reading a crystal ball now. There will be problems in your future if you go on and take more courses in algebra, where you are going to go through a process very similar to this, trying to determine if a particular linear expression, now that's linear because if I set y equal to it, I'd have a straight line. It's linear to the extent the degree is 1, x to the first. What we create is a thing called synthetic division. It looks a lot like the short division I was representing a moment ago. And so what I would do is simply look at the 3, and I would look at the 1, the negative 6, and the 9. and that's all I'd look at. So it's synthetic in the sense that you don't see the variables. And what I would do is create a process now. Instead of putting the numbers up here, I would put a number here. So I would say I'm starting with the 1, and 1 times 3 is 3. That gives me a -3, and -3 times this 3 is -9, and that gives me a 0, and therefore I know x minus 3 is a factor because I got a 0 at the end here. So what it looks like is taking the coefficients and forgetting about the variables. And I just illustrated here the very process that I went through in this problem. Now, if I don't get a 0 in this last part, then I know that x minus 3 is not a factor. So I want you to realize that there's a way of reducing this to a kind of short division, and by doing it in this way, I can decide whether or not the 3 works, and this is telling me that x minus 3 then is a factor in the process. So this will, again, be called later on synthetic division, and you actually end up doing something like this in, somewhere around Math 121, 122 in pre-calculus. So you're building on this whole idea of a division process with polynomials to, in a way, factor something into a product of linear factors. I don't expect you to hold any responsibility to that right at the moment, but it's a kind of advanced organizer. You would be using this process later on. If I look at something like x squared minus 9, and I want to write it as a product of linear factors, then I'm expecting, again, you recognize this is the difference of 2 perfect squares, and you have to, at some point, remember that that came from this kind of product. So we work backwards from memory. There is no shortcut for it. If you know the trinomial perfect square, then you should be able to, seeing the trinomial perfect square, get the factors. If you recognize the difference of 2 squares, you should be able to work backwards and get the factors. And we call that factoring. So we typically put an equal sign here and an equal sign here. The question, of course, why do we factor 1728 into a product of primes? And part of that answer came to finding LCDs. And in the same way, when we combined, or will combine, fractions involving variable expressions, we're going to find LCDs the same way. So that technique is part of the justification. Another part of that answer is going to involve what we call an equation, and I'm going to contrast that to a polynomial. To say that I have x squared minus 9 as an expression and want you to write it as a product of 2 linear terms, or factors really, is one thing. But there is a related problem, and I want to make sure right now you see the difference between these two. This is an expression. Now it happens to be a binomial. It's of degree 2. I can write it as a product of 2 linear factors, and with no particular justification other than I can do it. An equation is going to involve having 0 on the right side. And what we are going to try to do ultimately is use this ability to factor as a way of finding the answer to what numbers will make this a true statement. Now you can eyeball this and say, gee, a 3 works. A minus 3 works. And you can see immediately that there are 2 solutions to that problem. But if I go ahead and write it as a product of 2 linear factors, the question then is raised, when will a product be 0 in the real number system? And the answer to that is when one of the numbers I'm multiplying together is 0. So a product is 0 when I have 3 times 0, or 0 times 8, or 0 times 0. But certainly, as long as one of the factors is 0 in a product, the answer will be 0. Well, when will this product be 0? Well, when x minus 3 is 0, or x plus 3 is 0. And so we actually formalize that. And we say one of these two statements has to be true. Well, that's just then pretty much an observation that if this must be 0 or this must be 0, then that says x is equal to 3 or x is equal to minus 3. And we call that solving an equation. So that's why we're doing the factoring. Now, we're going to have a whole section on how to do that. But for the moment, I'm trying to give you some idea of why we are going through this process. So I have, in a way, leaped ahead into future material. And it brings up a number of questions that get addressed. You've already seen the problem of solving a linear equation in one variable. 2x equals 6. That's a linear equation in one variable. And you know that 2x equals 6 has a solution of 3. One solution. Now this is a second degree equation in one variable. And what you note is there are two solutions. Okay. Now I'm going to go back to a question, and I don't remember just where it came in, but at some point we got into, are there other numbers than real numbers? And this idea of seeing a pattern, and I've tried to illustrate for you in a number of occasions, patterns that are there in mathematics. The idea that a linear equation in one variable gave you one solution, a second degree equation in two variables gives you two solutions. The obvious question, are you guaranteed anytime you see a second degree equation in one variable, are you guaranteed two solutions? And the answer to that is not in the real numbers. Change this to a plus 9. X squared has to be positive. 9 is positive. X squared plus 9 would be the addition of two positives, and that would give me what? Not a 0. So if you're in the real numbers, that wouldn't seem to hold true. This pattern, second degree two solutions. That's why we create the imaginary numbers or complex numbers so that you can say, if you have a second degree equation, two solutions. One solution for a first degree. So if we have a third degree equation, x cubed minus 1 equals 0, then we'd expect three solutions. And in fact, that general idea of guaranteeing that an nth degree equation in one variable will have n distinct solutions became a very famous problem. And Carl Friedrich Gauss, at a very tender age, addressed that problem as a doctoral kind of dissertation and became a very important theorem in algebra. So that's the kind of thing we're doing. It all ties together, and that's why we're worried about the factoring. So with that said, I'm sort of getting ahead of the game considerably here, but it'll at least help you see why we are going in a particular direction. When we factor, this particular expression, I guess you can see right here, is a very typical one, but there are some that are much less difficult. What I have in mind is saying, let's say instead I had 3x squared minus 29. 27, how about that? 3x squared minus 27. So, Debbie, I'm going to leave that there for a moment, and I'm going to go to the sideboard, and we're going to sort of jump back and forth here a little bit. But we'll just leave that on the board. We looked at x squared minus 9. Now I'm asking you to consider 3x squared minus 27 and see how that looks different than what we've been talking about. So here goes. The 3x squared minus 27 is what we have on the board. And what I want you to realize is that there's a common factor in each of these two terms. In fact, there's a 3 that if I think of the distributive property can be brought out and write it as 3 times x squared minus 9. We call this a common factor. And in fact, we're going to use the initials GCF, greatest common factor. There's no larger number that I can pull out of those two terms. Now, it so happens I could, if I remember about the x squared minus 9 as being the difference of two squares, I could then factor completely. And so you will find the particular language that we talk about as factor completely, meaning first, take out a greatest common factor if possible, and then whatever is left, try to again factor. Now notice, sometimes all I can do is take out the greatest common factor. Let me contrast 3x squared plus 27. The 3 is common to both terms, agreed? But in this case, all I could do is take out the 3, and I cannot do anything to what's left. There's nothing you can do in the real numbers to the sum of two squares. You can't break it down further. The difference of two squares allowed me to go further. So Debbie, I'll leave that up there on the screen for a moment, and I'll go back, and what I'm going to do is use the document cam here in a moment, because this goes under a kind of generic problem that's illustrated for you on the 291 page, where I look at the idea, in fact 290, and again I'm a little bit concerned about how well this reads, but this is on 290 where you're asked to find the GCF, the greatest common factor. And of course the idea is to try to list the common factors, and an example, if we'll come off there for a moment, of such a problem is illustrated on this example right here, where you have 3m plus 12. Now, I don't know, I mean, it's certainly true that you can factor 12 into 3 times 4 and 3 times m for 3m, but there isn't anything that really dictates to you 3 and 4 more than 2 and 6. So when you look at what we have there in that expression, and I'll point to it here with a pencil, when you're looking at this 12, why go 3 and 4 instead of 2 and 6? And the only justification is there's what? A 3 here. So to take that idea that you write each part in a factored form has to involve some insight on your part, some common sense. There's no point if you have 3m of looking at 12 as 2 and 6. It's a nice exercise, but it's not particularly relevant. So in that sense, intuition, and I don't know what common sense necessarily implies to you, but it's something that I hope is self-guiding if you look at the problems. Now, in the same way, if I look at a little more complicated expression, this is on 292. Now, I have 3 terms. This is an example 3, I believe. We have a 20m to the 5th, a 10m to the 4th, and a 15m to the 3rd. What I hope you see is a common 5. Now, you technically could write 10 as 2 times 5, that's in primes, 15 as 3 times 5, but 20 in prime form is 2 times 2 times 5. I hope you see the common 5. Also, I hope you see the m to the 3rd that is common in each part. So the question that really gets raised here, when you have a problem like this, how do you take what you recognize, go from that step a little bit further? Okay, Debbie, let's come back to the document cam. And I want to leave that up there for you to see for a moment, and I want to rewrite that expression up here. We said we had, and I need it on the screen long enough for me to write it, 20m to the 5th plus 10m to the 4th plus 15m cubed. So as we cut to the board now, the 5, I hope everybody sees, is a common factor. There isn't a larger one that you can get. I'm hoping we don't have to do prime factoring to see that. I hope you also see that m cubed is the common variable, and we're focusing on what? The smallest exponent. So I'm arguing that 5m cubed is my greatest common factor. Now, if I remove that using the distributive property, the question I'm asking, what has to be left? So if I were to multiply, I would end up with the trinomial I had at the beginning. You're sort of reversing a process. Now, I'm hoping you can see the 5m cubed, and in your head, divide that into 20m to the fifth, and automatically see 4m to the second. And in the same way, that you would see 2m and then a plus 3. Now, if you can't see that, you're more or less forced into the following, which if you are forced into this, you're going to find yourself at a bit of disadvantage, but I'll write out the step to make sure it's clear what I was doing. That's going back to what we did in a previous section, correct? And you would sit there and cancel. And I hope you see immediately you would indeed get 4m to the second out of the first one. 5 into 20 goes 4. M to the 5 over m to the third is 5 minus 3, hence m squared, and likewise down. If this doesn't appeal to you, then of course you could argue that you are taking 5m cubed into 20m to the fifth plus 10m to the fourth plus 15m to the third, and I could do the long division you practice in the homework that I just returned. But I hope you realize if I have to resort to this, I'm slowing myself down enormously when I expect you to be able to do this in your head. But if you're having trouble seeing this trinomial in the parentheses, then think of doing one of these two until you get more comfortable. There's an obvious question unaddressed here, and that is this trinomial simplified? That is, can I factor any further with this particular trinomial I have here? And that is going to be a bit uncomfortable at the moment. We'll come back to that. That's what we're going to have to address later. For right now, we're just going to follow the directions, which were to factor out the GCF. That begs the issue. You factored out the greatest common factor, and whatever's left is left. Period. End of story. Any questions on what I've got there as a process? Okay, again, remember what the intent is, and that is to try to write expressions in a factored form. In the future, we will use that as a process to add fractions and solve equations. For right now, it just may seem like a certain exercise in symbolic manipulation for the sake of doing it. But you do need to develop a kind of skill level that allows you to do it quickly. So I'll leave that again. And then I'll be going up to the document cam, looking at other expressions of a similar nature. And of course, there comes a point in which you may be asked to first combine some terms. Now, let's see if there's anything here that I can put together to help with that. And I don't see a particular problem in that structure. Let me look at the homework and see if there's anything there. No. What I have in mind is you might get an expression where you first need to combine terms. So, Debbie, if you could go back to the problem I have on the board there on the side, and I'll try to, the second one, the far right, I'm sorry, the one on the far right. But what I have in mind there, and I'll just write something above it to explain what I have in mind. Let's say that I had 20m to the fifth, and I had plus 3m to the fourth plus 7m to the fourth plus 15m cubed, you understand that the first thing you want to do is simplify. Combine like terms. Once you combine like terms, then the idea is to take out the greatest common factor. So simplify first, then take out the greatest common factor. And that sort of goes in the process because there's another type of problem, and I have mixed feelings about this. It's called factoring by grouping. And here, as soon as I get this focused a little bit better, is the process. This is Objective 3, page 292. To factor by grouping. And this is not an obvious kind of thing. I'm going to leave that problem there, and we're going to talk about the process involved here. I'm going to illustrate it first. We have 2x plus 6, and then I believe I have ax plus 3a. Now, if I look at that as a problem and ask you to take out a greatest common factor, your first impression might be there isn't one. However, you could look at this by pairs of terms and say, well, I could do something in each of the first two terms. There's a greatest common factor there, which is 2. So I'm going to have 2 times x plus 3. Now, there's nothing right at the outset of this that's going to say this is motivated. This is more like, okay, here's another type of problem. Why would you ever think of this? I'm going to try to answer that in a moment. But if I look at the next pair, do you also see that the distributive property could be applied here and see that I have a times x plus 3 again? I had a common factor. Now what you're supposed to do is have an aha experience at this point. You're supposed to see a common factor again. That may or may not appeal to you. In which I could argue, well, x plus 3 is a common factor, which I can now remove and have what left by the distributive property, the 2 plus a. And now I've written a 4-termed expression as the product of two binomials. Now that sort of sits out there in the fringe as not so darn obvious to do. And what would motivate that? Okay. That is part of our dilemma. Now, I hate to leave something like this just sitting there and saying, well, this is just part of the rules you have to learn. Let me try to put it in some kind of context. Okay, let's look at a trinomial. X squared, and I'm going to have that as x squared plus 4x plus 3. Okay. Now, the question is whether I can see this in some way that I could break it up like this was broken up. Now, I'll tell you right now, this is straining at things a bit, and there are better ways of doing what I'm going to illustrate. But many authors, writers of textbooks and such, feel that this is one approach to the problem I addressed earlier. And Debbie, what I'm going to ask you to do is where I had the x squared minus 6x plus 9 on the front board. It's about center, and I wrote it as x minus 3 times x minus 3. If you can come to that for a moment. That x squared minus 6x plus 9, I ask you to recognize in a particular form. And I said I wanted you to see that as a trinomial perfect square, and you knew that came from x minus 3 times x minus 3. Very special case. But we wrote a trinomial as a product of two binomials. Now back to the sideboard. The question, can I write this as a product of two binomials? Now, what you have to do is get a little bit clever as how you rewrite it if we're going to take this attack. And what I'm going to do is break up the 4x into 3x plus x. Now, at the moment, there isn't a thing in the world to motivate that, other than I know I can write 4x as 3x plus x, but who gives a rip? Well, what I'm going to note now is that x is what? A common factor of the first two terms. And just for the sake of argument, the only common factor for the second two terms was a 1. Do you get the same aha experience that you were supposed to get up here? I tried to rig this so you have the same aha. You are not seeing the x plus 3 that is in both of them, hence aha. So I take out that aha, and what do I have left? An x plus 1, and using the same logic that was going up here, by a clever decomposition of 4x into 3x plus x, I now have a way of saying this trinomial is written as the product of two binomials. That's where the text is going. Now, there is nothing at the moment that's going to suggest to you that 3x plus x was a reasonable way. Why not 2x plus 2x? Or 1x plus 3x instead of the 3x plus 1x. That would have worked, by the way. But there's nothing that tells you what's going to work there and why. So, but this is where the text is going. And this isn't a bad thing to know, because it's one of those little tools you should learn how to use. Now, in this analogy, some of the things we're doing here are little techniques which you're supposed to learn how to use so that if you ever had a problem that would come up, you might use this tool in the tool chest you have available to you. It's not a bad analogy. It just leaves you out in the lurch. And the question, is there maybe a better way of doing the problem? And the answer to that will be a resounding yes. And the FOIL technique is what we're going to use. But this is a powerful technique that you at least need to have some comfort zone that you can use. And if I look at the top of 293, you can see where, and again, this is driven in a sense by not giving you any justification, but notice how the original problem might have been better written as m squared plus 8m plus 12, playing the same game. So think of what you're seeing as m squared plus 6m plus 2m plus 12 having originally been m squared plus 8m plus 12, and then you would have been motivated in a way that nobody would explain to you at the moment to break it into 6m plus 2m. But now notice, having done that, how I can factor out a common factor in the first two and the last two, and then get this aha experience in blue this time. A blue aha. That's like a brouhaha. A blue haha, and that gives us m plus 6 times m plus 2. There had to be some levity in that. What your text is trying to, see, what's the right phrase here, convince you to do is as following in this process: factoring by grouping. Group terms, factor within groups, then factor the entire polynomial, and if necessary, rearrange terms. Well, it goes under the guise of, when you see a trinomial, can you cleverly regroup and find the product of two binomials that will allow you to end up with a very nice factoring. Now, I'm trying to see what we have here. I don't like that. Let's see. Let's see if I can get something a little bit better here to illustrate the point. On page 295, because I don't want you to do this in the vacuum that's intended here. Okay, we're on page 295 and I'm looking at 64. I want you to see what's not written. In 64, what is not written is what I'm going to write on the board first. M squared plus 7m plus 10. Otherwise, what in the name of heck is going to determine for you that you should then see this as m squared plus 5m plus 2m plus 10? Do you understand the question I'm raising? Now let's say that again. I didn't catch it.
It's kind of like showing you the option, like the book is trying to like kind of train you in a way to like.
Yeah, they're trying to set you in a mindset. I was trying to come up with a word before, and we have. If I were trying to convince you of something in a political sense, and trying to change your whole attitude about the world, we have a name for it. What? Okay, persuasion. To train your mind to think in a different way. Yes, brainwashing. That's sort of the thought that came to my mind. We're trying to get you to see things in a particular way you would never have seen this way before. But unless you have some sense of why you're going to do it, or lead into it, you're never going to get to this middle step, which is critical to the process of what we are calling factoring. So the question, what is going to force you into a 5 and a 2? Any thoughts?
5 and 2 both go into that 10.
You got it. The 1 and 10, the 2 and 5 are what? Factorings of 10. That is probably the worst writing I've done in a long time. We'll blame it on the chalk. There are 1 and 10 and 2 and 5. So you might have said, well, I'll try this, or I might try what? Now, one of these is going to be productive and the other isn't. Now, you're being given this first one with the 3-star or 3-check credit, and this is a zip, nothing going for it. But look what happens now as I look at these two different results. The first one, do you see the m that's in common with the first two? So we have m times m plus 5. True? And then you see the 2 in the next group. So this is considered a productive insight because now you get the aha. You see the same thing. And then you know you're going to take that out as a common factor and be left with what? The m plus 2, and lo and behold, you went from a 4-termed mess to a product of 2 binomials, which is good. Because I have it in sort of a prime factored form. Now, did it work very well here? If I look at this one, I'm going to have m times m plus 1. That's nice. And then I'm going to have what? A 10. I guess I have a double 1 there. I don't need that. A 10 times m plus 1. And that is going to work, but it wasn't the original trinomial. This will work in the sense I'm going to get m plus 1 times m plus 10. But note, the 10m and the 1m didn't give me what? The 7m. So even though this works technically, it doesn't give me the middle term I need. So when I look at these factorings, it's clear that certain ones are better than the other. What catches your eye about the 2 and the 5? It happened to work with the 7, where the 1 and 10 only works with what? An 11. Okay, I can't let that go. So let me take one step further. If I know that this has to, if I'm going to make it work, it's going to have an m and an m. That's the only way it'll work, to get an m squared. And I have to have a 10, and the 10 can only be done by a 2 and a 5, or a 1 and a 10. Then the only one place I can get that 10 is having it at the second part of each binomial. So I have a choice. Either that or this. Those are my only choices, correct? To get a 10? Now the question, which one of those is going to work? Well, that's where you play the happy face game. FOIL. Because all you're worried about is the outers and the inners now. The outers and inners, 2m and 5m, give you 7. Here, the outers and the inners give you 11. Which one's good? The 7. So I put my 2 plus signs here and say that is the correct answer. That is the technique we're going to use more than we are this regrouping process, which to me is somewhat, well, it slows things down badly. So we're going to depend on FOIL more than we are in terms of the process illustrated in this set of problems. Let's go back to the document cam one more time, Debbie. The next one, y squared minus 6y, so that's number 66. So let me write that one down. Y squared minus 6y plus 4y minus 24. What do you think the original problem would have been that you would go to this particular grouping? Y squared minus 2y. All you have to do is simplify this. Y squared minus 2y minus 24. Do you see that those are the same? Mm-hmm. So we're doing the same problem. Now what are we going to do here? We're going to take y as a common factor, and here I'm going to take 4 as a common factor, and then you see what? The aha with y minus 6, and you're left with what? The y plus 4, and you have the factoring completed. Again, whether or not you would see coming from here this particular trinomial, I don't know. But if I follow this concept of looking at the factors up here, what are the factors of 24 I can use? Well, obviously the 124, 212, 38, 46, if I just keep the order going, if you don't mind. Does that get them? Now note what I ended up with down here. I ended up with a product of a difference and a sum. So when you do inners and outers, I'm going to get what? One negative, one positive. So in essence, I'm talking about finding a difference that's going to give me a 2. Okay, here are the possibilities. Which one of those possibilities gives me a difference of 2? The 4 and 6. This gives me a difference of 5, a difference of 10, a difference of 23. So this idea of breaking the last term into a product of two numbers and then looking at either a sum or a difference. Here it was a difference, gave me the 2 I needed. Up here, it was the sum of the 2 and 5 that gave me 7. How do I know if I have a sum or a difference? Here I had a negative, hence difference. Well, both of these are negative. I better be careful there. It's really this last one was negative, so that told me the difference. Here, see what I can see up there. Okay, we can see it up here. I had a positive 10, and that told me I had to have a sum. So I look at the last term. If it's positive, a sum. The last term is negative, a difference. So what I'm very gently, you may not argue that quite the same way, I'm gently trying to get you to see that this process of grouping into 4 different pieces can be done more efficiently by cleverly looking at the factoring possible in the last term. Now, by the way, that's only going to work if the first term is 1 something, 1x squared, 1y squared. If this becomes different than a 1, what I've told you so far isn't going to work. So we'll leave that there, and I'm going to go to a second problem that was in your illustration of what happens. This is on page 294, in which, let's see if I can get that so it's not so skewed on you. Okay, here's the problem. This is 294. Now notice what in this case. We got x's and y's both, and so this is not going to lend itself well. I'm going to show you the final answer. I'm just going to slide over. In the bottom of the screen, you can see the final answer at 2x minus 3 and y minus 4. To see that with the process I just tried to illustrate using FOIL is not going to be an easy reach there. But you also aren't going to see a problem like that very often. That's, from the author's point of view, a bit more of screwing things up unnecessarily. I'm going to look at a version of this that's a little more realistic. This is on page 293. This, if I can get it centered and lighten it up a little bit. How does that come across? This is example 5. Now that's more realistic. You have an x squared, you have a y squared, you have an xy. This is a little more typical. Still, you aren't going to see it all that often, but a little more typical in the process. What I'm trying to do is to find common factors in this process. Now, what is involved here, and this is what Lyle and Hornsby are trying to get you to see, you have to make some choices. Grouping 10x squared and minus 12y squared does not get you to aha. So let me slide over and show you what they get. Here's what you have so far in the solution. And there's no aha at this point. So you punt. So let me come down what we're watching in the screen to save me writing this on the board. Here is a new arrangement at the bottom of the screen. And if you take this arrangement and hunt for the greatest common factor, and that's illustrated here, suddenly you get very close to the aha. But as you note, the 5x minus 4y and the minus 4y plus 5x aren't quite in the same. There, we can see them both better. I've shaded it. And you see the 5x minus 4y in a disguised form, and now you see the aha and the final product at the bottom of the screen. Now that one is a little bit more difficult coming off there. That's a bit obscure too. I mean, what we're going to be doing right now, for the most part, the worst case scenario, I'm going to illustrate in a different kind of problem, and let's see what I can do here. Okay, let me do something to anticipate where we're going. I would like to look at a problem that actually comes from the next section to illustrate the idea I have in mind. And it's still not where I want to be, so let me go a little bit further. Here we go. We're looking at something like this expression. Now this actually is a little bit further on. But 2x squared plus 7x plus 6. Now what's different about this from what we've been talking about a few moments ago? The 2 is in front of the x squared, right? Now, by the way, if you want to know where the devil I am, I'm on page 303. But I need to look ahead a little bit to give you a better idea where we're going. Here's the expression, 2x squared plus 7x, and that just didn't, I should have been watching the board better. 2x squared plus 7x plus 6. Now, the idea in a problem like this, 2 and 3 is still out here, right, as possibilities. And I have a 2 here. So what I'm going to consider is something like this. As one possibility. Another one, let's see what else I want to do here. 3 and 2. And that's not looking so hot here. And so what I'm going to think about for the moment is maybe 2x plus 3x plus 4x plus 6. And let's see if we can get anything out of here. This is x squared, I'm sorry. So I'm going to have what? X times 2x plus 3. And here I'm going to have a 2 times 2x plus 3. So by grouping in a particular way, and you notice I tried 2 different ones. I had this one and this one. Why didn't I go for this? Because there's nothing I can do with 5x plus 6. So by playing around a little bit, I then see the 2x plus 3 as what is common, and now I've factored with this process. This is a little bit more realistic than what you're being shown in some of the problems you're doing. A little bit harder, too. What I would see up here, by the way, is 1, 6, 2, 3, 1, 2. And that's the technique we're going to do, where I start looking at the factorings here and putting those together as a technique. That's not the time to show it today, but what we've done here is a technique that your text is still getting you prepared for. So with that, let's see what kind of homework you're going to do. So I've tried to give you a little bit of an overview. Nice transition there. I'm going to try to give you a little bit of an overview of where we're heading as we do this so it doesn't seem out of context. There are a bunch of problems. They start on 294, but I'm not going to do anything there until we come down to number 35. So we're going to start on 35. The others you might want to check some answers to make sure that you know what you're doing. But we're going to come down to 35 through 82 odd. Let's see if there's anything in the next page. No. 35 through 82 odd, and I think that keeps the number of problems under some control. So Debbie, we started with Rolling Stones with an obscure selection. What is your last selection?
Rolling Stones, also brown sugar.
Okay, something again new for you. So have a pleasant day. We'll see you tomorrow.